Welcome back to Mustang Physics. Today's topic, simple harmonic motion. So simple harmonic motion is sometimes called simple harmonic oscillation. So if you see this word, that just means something that is in simple harmonic motion. An oscillator is something that simply moves back and forth. So if you think about a kid riding a swing, the kid's a simple harmonic oscillator. If you think about the pendulum that runs a grandfather clock, um, lots of any mass attached to a spring can act as a simple harmonic oscillator and be in simple harmonic motion. So I want you to imagine this mass with attached to the spring, attached to the ceiling. If we pulled it down and then it was free to bounce back and forth and back and forth and back and forth, its position would go up and then back down and then up and then back down and then up and then back down. So we could trace out the path of a simple harmonic oscillator versus time. So if we had a mass attached to a spring, it would reach some equilibrium position and we would call that position zero. And then if we either lifted it up or pulled it down and released it, it'd start to bounce up and down and up and down and up and down. And I really recommend that you go look at FET, masses, and springs and play around just so that you get an idea of what simple harmonic oscillators kind of look like as they move. Well, this path that is swept out, if this paper were rolling and there was a pen attached to this, it sweeps out a sine wave. So the displacement of a simple harmonic oscillator looks like a sine wave as long as the restoring force is proportional to x. In other words, if you pulled this twice as far, it's twice as much force at that position to pull it back. If you pulled it 4 times further, it'd be 4 times more force. So the further this mass is from its equilibrium position, the more force there is pulling it back towards that equilibrium position. And of course, the reason why it keeps oscillating then is there'll be a force towards equilibrium until it gets there, which means it'll be moving really fast. So it'll go way past equilibrium position, then it'll get pushed back and it'll pop back and forth and back and forth. All right. Now, do be careful. Don't use the word vibration when you mean oscillation. Vibration's a little bit more random, and oscillation has a very predictable repeating pattern. All right, let's take a look at our next slide. Now, this looks like a really busy slide, but if we break it down a little bit, it's really doable. Let me zoom out a little bit so we can see it a little bit better. So actually, let's zoom in and kind of ignore the equations for now. How about that? All right. So this shows a mass on a frictionless table attached to a spring. And off to the right, there's a free body diagram of the forces on the mass at each position. And the positions are labeled A, B, C, D, and E. And on our graph, we are going to make a mark about A, B, C, D, and then E is the same as A if you look carefully at what it looks like. And what we're going to do is mark down what would be true about the position or the displacement relative to the zero position, its equilibrium position, where the spring would neither be stretched or compressed, and the velocity at each spot and the acceleration at each spot. So if we take a look at this first one, there's a force to the left and the displacement is positive x. So in all these diagrams, positive is to the right. So this has been pulled as far as it's going to move. That would be its amplitude to the right. It wouldn't have any velocity at that spot because it is just about to turn around and go back. If we release it at that spot, then remember there's a restorative force back to the equilibrium position where x is 0. And so the entirety of the time while the mass moved from position x back to 0, there's been a decreasing force to the left. The force to the left has been making it accelerate to the left, so it would have a negative velocity at that point. Now the force would be 0 because there's only a restorative force when the mass is not at the equilibrium position, but the mass would be moving quite quickly to the left because it had been pushed or pulled to the left the entirety of the time from position x to 0. Now, because it has that velocity, it's not going to lose that velocity until there's a net force to the right for long enough to make it stop. That's going to happen when the mass is to the left of the equilibrium position. So as the mass moves from this position in point B over to here in point C, it's going to be pushed slightly to the right at first, more and more and more as it moves further and further to the left, and eventually there'll have been enough force for enough time to make it stop for a moment. That will be its maximum negative displacement, which would be equal and opposite the positive displacement. Since there's no friction in this system, this oscillation would continue forever. That's the spot where there's the maximum force because it's the furthest to the left of the equilibrium position. That force to the left is going to cause it to start to gain speed on the way back. And so as it gets back to its equilibrium position, it's got its maximum velocity again, but this time positive. It's moving by the equilibrium position to the right rather than to the left. And then, of course, the force is going to switch as soon as it passes equilibrium and be to the left. And so it's going to start to slow down again until it stops when there's the maximum force to the left. So let's graph what that looks like then. Let's think about the displacement at first. That's the easiest. So A is maximum positive displacement, so up here. B is back at the equilibrium position. C is maximum displacement to the left. D is back at the equilibrium position, and E is back at the maximum displacement on the positive again. And the way these connect is with a sine curve, since a spring gives a force that's proportional to the displacement. Remember that the force that a spring exerts is equal to kx, where k is the spring constant and x is the amount that the spring is stretched. So since the force is proportional to x, that a spring makes the mass into a simple harmonic oscillator. Now let's think about the velocity. I've got that in blue, so I'll bring in my blue pen. The velocity, part A, is actually 0 because it has stopped whenever it's at its maximum displacement. Then it's pushed to that left, so it's gaining speed, gaining speed, gaining speed until it gets back to the equilibrium position. So in picture B, it's actually got its maximum negative velocity. Then by picture C, it's stopped again, so 0 velocity. Picture D, it's maximum velocity, but to the right, it's positive. And then picture C, we're back to 0 velocity. Now if we connect those, we get another sine curve. And just like all displacement and velocity time graphs that represent the same motion, I want you to notice something. The value of the velocity graph is equal to the slope of the displacement graph. So the slope right here of the displacement graph would be 0, and the velocity is 0. The slope of the displacement graph right here is very negative, and that is the value of the velocity. The slope of the displacement graph right there is 0, and the velocity is 0. And that's simply because the slope of the displacement graph is the velocity. Now finally, the acceleration is actually easier to think about in terms of the force on it. So notice that the vertical forces have canceled out the whole time. The weight cancels out with the normal force. So only the left and right forces that are exerted on the mass by the spring are actually the net forces. So remember that this is true, and x is measured from that equilibrium position where x equals 0, which is this spot here. So the further that the mass is to the right, the more the force is to the left. The further the mass is to the left of the equilibrium position, the more the force is to the right, because that's what defines a simple harmonic oscillator, is that there's a restorative force that pulls the object or pushes it back towards the equilibrium position. So it ends up being the flip-flop of the displacement. When the object is furthest to the right, the force on it is maximum back towards the left. When it's at the equilibrium position, there is no restorative force. That's where the force restores to. When the object is at its furthest to the left, the force is at its maximum, pushing it back towards the right. And so you can see the force, the acceleration graph, because it's going to be proportional to the acceleration, right? Force causes acceleration. The acceleration graph is just the inverse of the displacement graph. for that simple reason that whenever you displace a simple harmonic oscillator, there's a net force that's going to push it back towards that equilibrium position. So again, the slope of the velocity time graph is the acceleration. So if we take a look at the slope of the velocity time graph when it's changing speed very quickly, it's negative. That we've got a negative acceleration. At B, we've got this maximum velocity right here, but remember that's close to the equilibrium position where there's not much force, and so the acceleration is actually really gentle. So interestingly enough, a simple harmonic oscillator is actually accelerating the most when its speeds are slow, and it's accelerating the least when its speeds are high. And the rate of acceleration is constantly changing since the amount of force changes depending on where it is. It's an interesting thing for you to be able to think about, like, what if it were halfway somewhere? So if we think about the simple harmonic oscillator, and it's attached to its spring, and here's the mass, and it can get to negative x displacement, and x displacement is here, and it's somewhere in between. What would be true about its displacement at that spot, its velocity at that spot, and its acceleration at that spot? Now, if that's all you know, all you could tell me is the acceleration and the displacement. The velocity, you'd have to know, has it already gone out to negative x and it's coming back, or is it on the way? So depending on whether it's going this way or that way, that'll tell you about the direction of the velocity. But that velocity will be slower than it is when it's at the equilibrium position, and it'll be faster than it is when it's at its maximum amplitude. So you want to be able to answer questions about kind of these midway points too. That would correspond to this diagram in here to, let's see, negative displacement. So that is here-ish or here-ish. We don't know which because we don't know if it's on the way out or on the way back. All right, now these equations, this defines the period. Remember that frequency is 1 over period. So sometimes we want the frequency of an oscillator, not its period. And sometimes it's much easier to measure frequency. We can always invert that to put into this equation. Notice that it is dependent on the mass. The more mass it has, the longer the period, because its acceleration will be gentler, and the spring constant. Now, if the spring constant is higher, that actually makes the period smaller, and that makes sense. If the spring constant is higher, that's going to pull the mass back towards its equilibrium position with more force, so it's going to bob back and forth more often. Notice what's not here, and that is amplitude. As it turns out, the amplitude of a simple harmonic oscillator has no relationship to the period, and that is simply because the more we pull it sideways before we release it, there'll be more restorative force. And so the distance gets bigger, but so does the speed. Those cancel out, and the time to get back to the equilibrium position is unchanged. Now, this equation is not on the AP Physics sheet. I've put it there because it's in the Giancoli book, but this relates the maximum speed it can have at the equilibrium position. That is related to the amplitude. The further you pull it, the faster it's going to go on its way back to the equilibrium position. Okay, so that is the simplest of simple harmonic oscillators and a good way to think about its motion. That's basically the kinematics of simple harmonic oscillators. Now let's take a look at a vertical one. A vertical one simply has the same sort of motion, but we have to be careful here. There's an additional force, gravity. So the equilibrium position is actually not where the spring isn't stretched at all. The equilibrium position is where the spring is stretched just enough so that the spring's force and the gravitational force cancel out. At maximum displacement, the force the spring exerts on the mass would be larger than gravity, so the net force is at its maximum up. And at the maximum amplitude above the equilibrium position, the force of the spring is the same amount, smaller than gravity, so the net force is back towards the bottom. Now, since a spring ideally gives a larger force, whether the rate of the force change is, again, proportional to that change in x, and gravity is a constant, the net force you see is just as big on either side because the force from the spring is going to increase linearly as you stretch it further and decrease linearly as it compresses. All of this is just a restatement of what we talked about with the one that was sideways. So again, this is another one where it's great to go use that FET masses and springs and play around with this. Within that simulation, you can also turn gravity off if you want the analysis to be a little bit simpler. But I would leave gravity on and think about how those forces interact. Remember, the net force is the thing that's causing the acceleration, not any one particular force. All right, so one more kind of simple harmonic oscillator is simply a pendulum. A pendulum is a simple harmonic oscillator, and the amplitude, again, doesn't matter. A pendulum only exhibits simple harmonic oscillation, though, if this angle is small. And that's because the restorative force sideways is proportional to mg sine theta, and sine theta is pretty linear as long as theta is pretty small. But as theta gets big, of course, sine theta is going to start following a sine curve instead of being linear. So for small angles, this equation works really well. Notice that the primary thing that affects the period, if you're on Earth, is the length of the pendulum. The longer it is, the longer the period. And G is related. That also means, by the way, that if we set up a pendulum and we measure its period and its length, we can actually use it to calculate G. And in fact, you can get really accurate calculations. So for a moment, let's take a look at this in action. I just want to show you that a pendulum with a short cord does in fact move back and forth much more often than a pendulum with a long cord. And if you have a weight attached to a string, you can try this for yourself. So let's flip the camera and flip it up just a little bit so that you can see what's going on in the room here. And I'm going to grab one of our plumb bobs from school. There we go. So there we go. You can see my plumb bob up against the wall. So I'm going to give this a little bit of a force to get it going sideways. There we go. And 1, 2, there's a period. One full swing. So 1, 2. And because this is on a cord, I can just pull it through my hand without really exerting any force on it sideways, and watch what happens to the period once I shorten the cord. You can see that it swings back much more often. So the length of the pendulum is the primary driver of how long its period will be. And so if you think about it, there's a lot of clocks that have something that looks like that, grandfather clocks in particular. The pendulum actually is the timekeeper, and its length is effectively how we set the time. So the way a pendulum and a grandfather clock works is there's a little mechanism that every time the pendulum swings back and forth, there's a little bit of energy given to it, just a little bit of push to make sure that the pendulum never stops swinging, because obviously frictional forces would cause it to stop swinging at some point. That's why every once in a while you have to go and lift up the weights in a grandfather clock. The potential energy of the weights inside the clock is what gives the pendulum a little push, but that push affects the amplitude, which does not affect the period. So that push just keeps the pendulum swinging and keeps the grandfather clock keeping time. If the grandfather clock is keeping time either too fast or too slow, then we can shorten or lengthen the pendulum as appropriate. Okay, let's go back to the notes here. Flip this over, you can see it. There we go. And think about a couple more ideas, and then we'll be done. All right, so sorry about that, just trying to refocus, not flip you over. There are some other situations that exhibit simple harmonic oscillators. So there's kind of inverted pendulums where you've got kind of a rigid object. So you might think about maybe you went to the park when you were a little kid, or maybe when you were a little bit bigger, and there's this big, massive spring, and then there was like a little duck or a horse or something like that, a little spot you could sit, and you'd start swinging back and forth. The period of that, it's like a pendulum, so there's kind of an effective spring constant when you bend the spring this way. So if you've ever ridden one of those, that's kind of an inverted pendulum. A tuning fork's like an inverted pendulum. So when we play a tuning fork, this thing vibrates back and forth and back and forth. There's a kind of an effective spring constant that brings it back. A string on a violin acts like a simple harmonic oscillator. If we pull the string sideways when we pluck it, then there's a restorative force back to the center, and that's why it vibrates back and forth at a particular frequency. Even molecular bonds behave this way, and if your shocks are bad and you push down on a car or it hits a bump, then the car will bounce in a sine wave, and that's because your car is a mass suspended by springs, so it acts like a simple harmonic oscillator also. All right. Lastly here, we'll talk about energy. This is the last page in the notes. You might have to skip ahead. You might want to just recall that the potential energy stored in a spring is any potential energy on the AP test that's abbreviated U. So the potential energy in a spring is equal to 1/2 kx squared. So that's not a linear with x. It is a power of 2 of the displacement. And remember that for a simple harmonic oscillator oscillating vertically, that the potential energy gravitational is mgy. And of course, this simple harmonic oscillator can have kinetic energy also. It can be moving, so it's got 1/2 mv squared. So if you decide to solve this simple harmonic oscillator problem from an energy perspective, if it's oscillating sideways on a frictionless surface, then you'd only need these two equations. But if it's oscillating vertically, you might also have to include the potential energy if we are not ignoring the effects of gravity. If you do that, I'd recommend for the spring that's oscillating vertically that you set the zero height of y equal to the lowest spot. Otherwise, you're going to have negative amounts of energy, and that's crazy. It just doesn't help you really understand the problem very well. It makes it mathematically more difficult. The equilibrium position where it's 0, remember that if the mass is here or here from equilibrium, it's going to have potential energy because the spring is either stretched more than it would typically be at equilibrium, or it's compressed more than it would be at equilibrium. Since x is squared in the equation, whether it's positive x or negative x, or positive x and negative x, depending on which way you set positive, there's potential energy that's positive either way. The kinetic energy would be greatest, again, at the equilibrium point, since remember, the speed of the simple harmonic oscillator is going to be fastest as it swings by equilibrium. All right, hopefully that's enough for you to start thinking about how simple harmonic motion works and start to try those problems in the book. Good luck with those. Next week, we'll be doing a lab where you have to design your own experiment around a simple harmonic oscillator, but we'll practice a little bit before we get there. Hope you've enjoyed this. We'll see you next time.